Hello students, welcome to Sarasa classes. Now in this section we will be discussing the CX disconnection of amines. So over here I must say that amines cannot be synthesized the way we have synthesized the ethers and the sulfides. The reason mainly being that amines when reacted with ammonia, it is difficult to control and stop the reaction to only primary amine, because in relation to ammonia, primary amines are much more reactive and compete with the ammonia. So this will further react with another molecule of alkyl halide, leading to the formation of secondary amine, which further reacts with another molecule of alkyl halide to form the tertiary amine. Tertiary amine being much more reactive than all the amines in organic solvent, okay, will further react with another molecule of alkyl halide to form the quaternary ammonium salt. So this is the problem for which amines cannot be directly prepared by reaction of an alkyl halide with a ammonia. So we have to consider different pathways now by which we will be preparing such amines. So let us first consider the synthesis of over here primary amine, and we will say that primary amine can be prepared by the following pathways, that is by reduction of amides or reduction of cyanides, okay, and basically reduction of cyanides can be used for synthesis of unbranched amines, which we will see how this is possible. And for disconnecting these amines, what we consider is the functional group interconversion of the CH2 NH2 to C triple bond N. That is what we have to consider. Similarly, for other pathways, we will say reduction of oximes, imines. These are pathways by which we will say we can prepare branched amines. So now we can see that there can be two types of primary amines, that is branched primary amine and unbranched primary amine. For unbranched, we are using cyanide reduction, and for branched amine, we are using reduction of oximes, or we will say imines. Besides this, we can even reduce the alkyl azides to provide us the amines. Okay, so let's consider one such general retrosynthetic analysis in which we have RCH2 NH2. So if we do the functional group interconversion over here we will simply convert this into a nitrile, and then we will disconnect the bond, and we will write R plus and Cn minus. Obviously, the synthetic equivalent for Cn, if we say the derived, then it is NaCN minus, which can further be made from HCN, which is the synthetic equivalent. And for the R plus, obviously, it is electrophile which has to be joined to a good leaving group, and there we will say let us that be iodine. So when we are considering the synthesis, we will say it is the Ri reacting with NaCN, and we will be producing RCN, which when reduced with lithium aluminum hydride followed by workup with water gives us the target material molecule, which is obviously RCH2NH2. Similarly, let us consider the analysis of ArCH2NH2. In that, we will say if we do the FGI, we will say it is going to be giving us ArCN, and if we do the FGI of this one, then obviously we will say let us consider ArNH2. Now, while we do the synthesis, the ArNH2 can be converted to the diazonium using nitrous acid at a very low temperature of 0 to 5 degrees centigrade, which when treated with cuprous cyanide will provide us ArCN, followed by reduction with lithium aluminum hydride. The workup again done with water gives us ArCH2NH2, the desired target molecule. Again, if we consider a molecule like this, let us do the FGI, and we can say that it is connected to the azide, whereas the azide can be further cleaved, okay, over here. So this is basically a CX type disconnection in which this is produced along with, or let's say it will be not disconnect over here, but if we do the FGI, we can convert this into simply into a halide. Okay, so in the synthesis part, what we will say that this, if we react with sodium azide, okay, obviously in presence of DMF, which will prefer or favor SN2 type of reaction, so it will be the alkyl azide that will be found, which on treatment with lithium aluminum hydride obviously will give us the desired amine over here. Always remember, whenever we use a organometallic reagent or reagents something like as lithium aluminum hydride, the workup has to be done with the water molecule. Similarly, we can also use phthalimide for the synthesis of primary amines, and how one can do that is I'm showing. So this is our phthalimide. This is another way of synthesizing this particular target molecule over here. So over here, if we are treating this with KOH, then we have the imide ion, which can be resonance stabilized into these carbonyl groups over here. So that is mean that is highly stable. Again, if you are using this alkyl bromide, we can think of a nucleophilic attack to this carbon via SN2 pathway that will lead to this intermediate molecule over here, as shown, which when treated with sodium hydroxide in presence of water will undergo amide hydrolysis and lead to the formation of the phthalic acid. Besides that, it will produce the desired target material as shown. So this is basically Gabriel synthesis of amines, which we are using over here. So having discussed the unbranched amines, let us consider the branched amines over here, in which suppose we have taken this molecule. Let us do an FGI. For branched amines, as I have discussed, we will be either considering oximes or imines. Now here we can convert this amine to a imine. We can use the 1,1 DIX, that is disconnection, and we can think of here two such positive charges and the NH. So this can be added to two protons, giving us the ammonia, or we can even call this to be as hydroxylamine. Either one can be used. And whenever we have a plus plus charge on carbon, I have said before that we will add oxide ion. So this will give us the desired ketone that was being used. So in this synthetic pathway, we can think what? That we have R1, R2, which is being treated with either hydroxylamine or ammonia, and that is leading to the formation of the oxime, which when treated with sodium cyanoborohydride, it will lead to the formation of the branched amine as shown over here. So out here we are going to use this to do a complex molecule. Okay, so let us consider the